Assalamualaikum and hi everyone. We are from Group 1. Today, we are going to explain about radiation and its history. My name is Nur Faruhuda binti Zulkafli and I am the first presenter.
Hi, I'm second presenter. My name is Nofati Ayuni.
Hi, nama Olivia.
Hi, I'm Siti Haja.
My name is Nur Faruhuda. Okay, what is radiation? Radiation is an emission or transmission of energy in the form of wave or particles through space or through material media. Did you know humans are exposed to radiation all the time? The radiation called background radiation is from natural radiation and artificial radiation. For natural background radiation, it is an exposure of naturally occurs radioactive from the environment, while artificial radiation is from human activity through the use and creating of artificial radiation sources. Okay. Cosmic rays, terrestrial radiation, and radiation from our body and food are the sources of natural radiation. For cosmic rays is the radiation that reaches the Earth from space. The Sun and stars send a constant stream of cosmic radiation to Earth. Since the radiation is from space, people in higher altitude either live on the mountain or travel by plane, they receive higher dose of cosmic radiation. The differences in elevation, atmospheric conditions, and Earth's magnetic field will give different amount of exposure. Okay, the picture here shows that the radiation exposure for people who live on the mountain is 2 times greater than people who live on the ground. It will show that when we travel by airplane, the amount of cosmic rays we receive is 4 times greater than when we are on the ground. For terrestrial radiation, the Earth itself is the source because soils and rocks are the naturally occurring radioactive sources that contains thorium and radium, and water also contains small amount of dissolved uranium and thorium. Organic matter such as plants and animals contain radioactive carbon and potassium. Dose from terrestrial radiation varies in different parts of the world because it depends on the soil concentration of uranium and thorium. The higher the concentration, the greater the dose received by the inhabitant. So the picture here shows the radionuclide that contained in the soil. Okay, so we can see that here we have radon 226, thorium 232, uranium 238, and uranium 225. We also show that we inhale radon 222. Okay, we humans have internal radiation, mainly from radioactive potassium 40 and carbon 14, which is naturally exists in bodies since birth. And radiation is introduced to the body by consumption of food and water that contains radioactive material. And as I mentioned before that we inhale radon 222, right? So the inhalation of air containing radon. Okay, the table here show the radioactive level that in our food that we consume, like rice, vegetables, milk. So show that mainly it consists of radium, thorium, lumber, lead, and potassium 40. Okay, for artificial radiation, we got 4 sources here, which are medical radiation, nuclear power station, nuclear weapon, and consumer product. For medical radiation is the radiation exposure for medical procedures such as diagnostic X-ray, nuclear medicine procedure, and radiotherapy. Radiation personnel and patients are the ones who usually exposed to medical radiation. Therefore, the limits of exposure for radiation workers are greater than public, while for patients there are no limit but the procedure needs to follow another principle, which is as low as reasonably achievable. Okay, for nuclear power station. Its major incidents from nuclear power station have released radiation into the environment. The nuclear waste account for a small proportion of background radiation. The incidents of nuclear power stations are like Fukushima and Chernobyl. Okay, for nuclear weapons, nuclear weapon is a device used in nuclear reaction to create an explosion which causes great destruction, death, and injury and has a wide area of impact. The explosion increases the radiation of the environment. And lastly, for the consumer product. Okay, in the early days, luminous dial watches is very popular. The production of the watches has exposed the radiation to the workers and consumers. Other than that, we have smoke detectors that also contain radioactive material, which is americium-241. The dose for both luminous dial watch and smoke detector are relatively small. Okay, the annual exposure we got from artificial radiation is about 0.6 millisievert a year. Okay, the pie chart here shows the contribution for natural radiation and artificial. Okay, as you can see here, 42% of radon is the largest contribution for the radiation, and nuclear industry the smallest one, which is 1% only. Okay, so you can see that it right. You mentioned here the natural radiation is contribute 85% to the background radiation, which is larger than the artificial radiation. That's all from me.
Hello, my name is Nurfati Ayuni. So I will proceed with radioactivity and type of radiation. So what is radioactivity? Radioactivity is disintegration of atom, a spontaneous process of unstable nucleus decay to stable nucleus and loss or release its energy through the emission of alpha, beta or gamma particles. Radioactivity is discovered by Henry Becquerel in 1896. So, how is this integration of atom occurs? First, let's get to know the atomic structure of an atom. Electron is a negatively charged subatomic particle that orbits around nucleus. Nucleus is located at the center of atom that consists of positively charged of proton and neutral charge of neutron. So, between positively charged proton, they push each other because of the electrostatic force, but neutron has a strong force that hold the atomic nucleus together and keep the nucleus stable. Nucleus needs a right number of proton and a right number of neutron to be stable because nucleus strong force only work at a short distance, which about a diameter of proton or neutron. Therefore, if an atom happens to have excess of proton or neutron in the nucleus, atom will simply fly apart because of the weak nucleus strong force. Therefore, to reach the stability, atom will eject or convert either proton or neutron by releasing particles or energy to form other element. Alright, how can we know an element undergo decay? We can know through its activity and half-life. Activity is an amount of radioactivity given by number of decays per unit. We can simply say that rate of decay. It is expressed in unit becquerel that is named after Henry Becquerel. 1 becquerel is equal to 1 decay per second. Half-life is a time taken for the activity reduced to half from its initial value. So, as the time goes on, the activity of radioactive element will be decreases. There are three types of radiation that emitted during radioactive decay. First, alpha radiation. Alpha radiation is a positive charged particle that represents helium, has 2 protons and 2 neutrons. Alpha radiation can highly ionize that can cause biological damage to human body if the radiation is inhaled, swallowed, or absorbed to the body. Alpha radiation has low penetrating power, therefore alpha can be blocked by a piece of paper. Second, beta radiation. Beta radiation is a negatively charged particle that has low ionization ability but high penetrating power compared to the alpha. Therefore, beta particle can pass through the paper but can be blocked by layers of aluminium. Lastly is gamma radiation. Gamma radiation is a form of electromagnetic radiation that has neutral charge. Gamma radiation has low ionization ability but has high penetrating power. Therefore, gamma can can pass through the paper, aluminum, but it can be blocked by the lead. If gamma radiation has high energy, it can pass through the lead, but can be blocked by thickness of concrete. Do you know that our body actually emits radiation? A human body typically has about 9,000 becquerel of radioactivity. It is about 100 becquerel per kilogram. Our body consists of radioactive elements of potassium-40 and carbon-14, which is commonly coming from the food that we consume. So we know that if we expose to the radiation, it can cause bad effect. But if we use the radiation with precaution, it can give us a lot of benefit. In medicine, radioisotope or radiation is used as a tracer for diagnosis or for treatments such as radiotherapy, while in industrial, beta radiation is used to control the thickness of paper during manufacture, and alpha sources is used in smoke detectors. Gamma radiation is used to sterilize and to kill the harmful bacteria in food. And lastly is radiocarbon dating, which is used to calculate or measure the age of organic material. Thank you.
Okay, you're most welcome. My name is Namong Olivia, and I'll be taking you through the history of radiation. So basically, I'll deal with X-rays and polonium and radium, and the rest will be discovered by my friend. So following this chart, we can see that X-rays fall under 1895 by Roentgen, and polonium and radium fall between 1898 by Maria Curie and Pierre Curie. The discovery of X-rays. These rays were discovered in the late 1895 by Wilhelm Roentgen. Roentgen was a professor at University of Wittenberg, Germany, and he began an experiment of discovering X-rays. He began it with an experiment which was already designed by Philip Leonard. Leonard had designed an experiment whereby he had replaced a glass wall of a tube with a thin aluminium window. Now, for him, he was targeting to see that uh, the cathode rays, which were already discovered, are let out from the tube. So that's where Roentgen started from. So using Leonard tube, Roentgen made an observation of fluorescence beyond the range of cathode rays. So he kept on wondering what really had caused this too much fluorescence. Later on, he discovered that there were some sort of rays which weren't cathode rays, and he couldn't define his name, so he named them X-rays. So these rays had the capacity to photograph the bones, and once people discovered that these rays can enter into, like, inside the body of a human being, so they started to make fun of these rays. They really wanted to see if they can see the inside of themselves. Publicly, Roentgen first demonstrated on Rudolf Albert von, who voluntarily surrendered to his arm to be used as a demonstration. The first medical use of X-rays was on 23rd Jan in 1896, and it was used to locate a piece of a knife in the backbone of a sailor. So history says that this sailor had been with this knife for quite some time. So when the rays were discovered, it was a chance for him uh, to see really where the position of this knife was, and it was discovered. So here in this picture, this is Roentgen, and then this was the first harm, which was imaged by the X-rays. So this is the apparatus, the first X-ray apparatus, which was used by Roentgen. Okay, so about the history of polonium. Polonium was discovered by Maria Curie and Pierre Curie in 1898. It was extracted from uranium ore, pitch blende, as it was too radioactive. So during their research, they really, because already uranium was discovered in a part of radioactivity. But then when they kept on studying the uranium ore, they really saw that this uranium was still too radioactive. So they asked themselves what was really inside in. In the end, they found out that this uranium ore actually had both polonium and radium, and they were such so radioactive. So on discovering polonium, it was named after Maria Curie's homeland, which is known as Poland. So this polonium comprises of isotopes that are radioactive, and the common one is polonium 210. It is a radioactive element whose atomic number is 84. So in this picture, you can see that this is Maria Curie and Pierre. So continuing with polonium on its properties, it is a solid metal with a silver color when it is in its natural state. It is very volatile. And then the isotopes are too radioactive. Like we said the previous slide, that the common isotope of polonium is 210. It is highly dangerous, but then it has a short half-life, meaning that its danger goes away so fast, but then after causing you the harm. So the biological half-life is 40 days and the physical half-life is 140 days. So as you can see here is that the polonium is actually really toxic if ingested even in a small amount. And then it can be used as a heat source. Being too radioactive, it produces heat. So in moon and satellites, polonium has been used as a heat source. And polonium is being used as an antistatic in the brushes which are used to clean the photographic film. So when we get to radium, this radium was still discovered in the same way like polonium and still discovered by the same person in 1898. So it is known to be one of the most radioactive substances and the common radioisotope of radium, just like polonium, they are radium 226 and radium 228. So in the decay theory, we can see that uranium decaying to thorium, then thorium decaying to radium 226 to radium 222. So all isotopes of radium are radioactive, just like the friend polonium. So radium decays to produce the radon gas. So another property of radium is that it glows in the dark. So before this radium was discovered to be such a dangerous substance, it was being used in the dark watch dials, and then in the night they could glow. And then another funny thing is that after the discovery of uranium, the ladies used to smear themselves with this radium, and then in the dark they could glow to look so beautiful, not knowing that they were risking their lives. And on part of radium steel, it was being used in toothpaste and then sometimes chocolates before its healthy effects were known. So, like I said, that radium decays to produce radon gas. This radon gas is used to treat some types of cancer, e.g., uterine body. So, did you know that when radon is breathed into the lungs, it can deposit radioactive particles which can damage the DNA, hence increasing the risk of lung cancer. We've seen that this radon is used to treat certain cancers, but then when breathed in, it can still cause lung cancer. So we have to get so careful when we are dealing with radon, such that we don't risk ourselves to getting uh, lung cancer. Okay, thank you. Bye bye.
Hi, I'm Haja. I'm going to explain a very brief history of the discovery of radioactivity. Henry Becquerel accidentally discovered radioactivity in 1896. His grandfather, his father, they are all conducted experiments on fluorescence and phosphorescence. Well, you might call it as their family obsession. Henry Becquerel was interested in uranium and its compounds. He thought that the phosphorescent uranium salts he had been studying might absorb sunlight and re-emit it as X-rays. So to test this idea, he wrapped a photographic plate in black paper so that sunlight could not reach them. Then he placed the crystals of uranium salt on top of the wrapped plates and put the whole setup outside in the sun. When he developed the plates, he saw an outline of the crystals. He took this as evidence that his idea was correct, that the phosphorescent uranium salts absorbed sunlight and emitted a penetrating radiation similar to X-rays. Seeking further confirmation of what he had found, he planned to continue his experiments, but the weather in Paris did not cooperate. Thinking that he couldn't do any research without bright sunlight, he put his uranium crystals and photographic plates away in a drawer. He opened the drawer and developed the plates on the next day, expecting to see a very weak image. Instead, the image was amazingly clear. The energy was coming from uranium itself. In 1899, Ernest Rutherford used two oppositely charged plates. He identified two components, positive particles, that are alpha, and lighter mass negative particles, that are beta. In 1900, Paul Henri Villard he discovered gamma radiation while studying radiation emitted from radium. In 1903, Villard's radiation was named gamma rays by Ernest Rutherford. Paul Villard studied the rays emitted by a radium sample. Gamma rays have no mass and possess no charge. The behavior of the types of particles as they pass through the electric field between two charged plates are studied by Villard and Rutherford. Alpha particles were deflected more slowly than beta particles, which suggested that alpha particles were heavier than beta particles. Gamma rays were not affected by a magnetic field. This is a photo of experimenters taking an X-ray with an early Crookes tube apparatus. The Crookes X-ray tube is visible suspended at the center. The man is examining the bones of his hand with a fluoroscope screen. The other man is taking a radiograph of his hand with a photographic plate. Both of them are using the same X-ray Crookes tube to perform two experiments at the same time. They are killing two birds with one stone. Its hazards were not known at the time. No precautions against radiation exposures are taken. In late 1896, Elihu Thomson performed an experiment to determine the potential harmful effects of X-rays. He is the first person to prove a direct relation between exposure and health effects. He purposely exposed the little finger of his left hand to the direct radiation from an X-ray tube daily over a period of a week. For the first week, there was no observable effect. After several days of exposure, the finger becomes swollen, sensitive, and painful. As for the result of the injury, he was convinced that the effect was caused by the chemical activity of the rays and issued a caution. One of his recommendations was do not expose more than one finger. The pictures show the hands of a radiologist in early years after repeated exposures of hands to X-rays and in later years just before he died of radiation-induced cancer. Well, not all bad news. The first successful treatment of cancer is recorded in 1899, basal cell carcinoma cured by X-rays. To treat basal cell carcinoma, total of 99 treatments was given over a period of several months. 30 years later, after treatment, the lesion can be healed with Röntgen irradiation. It's quite beautiful. By 1910, most workers using X-rays and radioactive substances were taking some precautions, such as lead rubber protective wear for operators, filtering the beam to remove soft X-rays, using a phantom to check tube rather than operator's hand, and shielding the tube to produce a collimated beam. The unfortunate early experiences eventually led to an awareness of radiation hazards for professional workers. Radiation safety will continue to play an increasing role in keeping physicians and patients safe.